Good morning, everybody. I hope that you can see our screen well. It should just be our pumps and motors application, hydraulic selection, and troubleshooting first page of my PowerPoint presentation. If you can't, please unmute and let me know. But we're just trying to see how this fits into the 1 hour schedule and see how it logistically works for these webinars. So hopefully this will be a nice tool for us to use to keep the training hours up for our operators. So I'm just going to start and go through the slides. This is something that some of you guys have seen before, but I think it'll be a good refresher course for our team. Also, if there's any interruptions, I know I was on a conference call a day before yesterday with Grundfos, and my wife and daughters got in my car and turned it on, and my Bluetooth kicked in, and they were in the car hooping and hollering and being somewhat inappropriate, and Grundfos heard all parts of it. So if something like that happens, I apologize. Hopefully we've learned our lesson, but that seems to be the fruits of working from home. So we'll start through the presentation. Okay, what we hope to accomplish. We hope to accomplish the discussion of several different types of pumps and what their applications are, the hydraulic designs. We'll spend a lot of time working through a pump performance curve and all the information that you can get from those curves, troubleshooting pumping systems using those hydraulic indicators. And then, as Dominica said, we're going to have some questions that'll pop in throughout. Part of the requirements for the continuing education hours is to have participation by including questions. So this will be the way that we're going to try to do that and see how that works. So you see all the different types of pumps that we have. We'll start with water. The first type of water pump that we'll talk about is an end suction pump. You guys have seen these out in the field. They come in close coupled, meaning that the motor is right against the volute, and frame mounted, which means that there is a shaft that goes between the motor and the volute with a coupling in between. These are for relatively low flow, low head applications, very simple pumps. The discharge is on the volute, can be rotated in any direction, but it gets its name end suction because the water comes in through the end of the volute, right at the end of the pump, and then discharges vertically, or however you have that arranged. To me, the most complex part of this is the piping requirements. There's an offset discharge, and it's not a straight through design. The next type of pump that we'll talk about is the horizontal split case. These are for high flows and relatively low head applications, even though you can get these in multi-stage, meaning there's more than one impeller. If you look here, I hope you can see my cursor. It gets its name because this part of the volute can be taken apart as a split case to access the rotating assembly. As you can see, this is a horizontal design, but it can be vertically mounted with a different type of bracketing installation guide, so that it can be put in a smaller footprint and the flow is straight through, which makes for an easy piping. You'll see these a lot in water plants, either for high service pumps if there are relatively low head applications, or backwash pumps a lot because you usually have fairly high flows in a filter and very low heads because you don't want to wash out the filter media. Next is a pump that we're very familiar with, that we see all the time in our area, which is a vertical multi-stage pump. We represent Grundfos. This is the CR series. They have very low flows and relatively high head applications. So it's perfect for our geography, where we have a rural area where we have very few people at times, but we have very high heads to overcome because of the topography. Multi-stage means that there are multiple impellers. As you see inside of this stack, each one of these impellers are stacked on top of another, which means that the flow comes in. The flow is not multiplied, but every time you go up through an impeller, you add additional pressure. So if each impeller gives you 10 feet of head, then every one of these is going to add 10 feet to the what comes into it. So as you can tell, the more impellers you have, the more pressure that you can create on the discharge side. These are very common. They're easy to install, very durable and long lasting, and the plumbing is very easy. There's usually either a threaded connection, a 125-pound connection, or a 250-pound connection, and the lay lengths are relatively short, so it gives you an opportunity to put them in a small area. Vertical turbine pumps are used a lot for raw water or high service pumps, sometimes for backwash pumps, but they're relatively high flows and high heads. They are a multi-stage pump. As you see here, each of these bowl assemblies have an impeller inside, and depending on the requirement for head, you can have as many of these as needed to provide the discharge pressure required to serve your purpose. These can be done in deep well installations. For instance, at Summersville, we have a deep well system where it's going down into a raw water pump at Summersville Lake. So it sits probably 100, 125 feet down below the level of the discharge head and pulls it out of the lake, and because the impellers sit down in the water and pushes it up through the column pipe into the discharge head and out into the system. These can also be used for a short set canned installation when we don't have a clear well or a well to pump out of, or a lake. We put a can in around the column and shafting and bowl assembly so that the water flows in, down in the can, up through the pump and out the discharge head. So those are the applications. As I told you, we can use it for raw water, which means that it's relatively clean, or clean water applications. Submersible turbines also are a multi-stage pump, but these are designed to go down into a well, into a casing. The motor is on the bottom and it stays submerged to keep it cooled. They can be real high head because of the multi-stage, relatively low flow, although some of the big pumps can get up to 1,500 gallons per minute. And they're usually installed with a pitless adapter to ease for installation and removal. So we'll move on to dirty water pumps. Some of the things that are not as fun to mess with. This one we'll start with is a submersible non-clog. These are high flow and low head pumps. They have to pass a 3-inch solid in order to be approved in the state. The requirement is because the purpose of this is to pass raw sewage, and they want to make sure that all of these are able to pass a 3-inch solid. Just so you guys know, one of the things that differentiates us and Flight is that with both either Grundfos, who we represent, or with ABS, we pass a 3-inch solid. Flight uses, with their N impeller, uses a cutting ring on the inlet of their pump and shreds their solids before they pass it. That doesn't really do what a non-clog pump is supposed to do, but they've done a great job of marketing and getting approval throughout the country. So that is a difference. There's positives and negatives about both, but I just wanted to let you know that that is a difference. Non-clog pumps are relatively low efficiency pumps because they have to handle the raw sewage, and they must stay submerged unless you get a very high efficient one with a cooling jacket, and then you can have a non-clog pump that is submersible, but it's called a dry pit submersible, and we'll see those. Grinder pump is the next one we'll talk about. These are much smaller pumps, up through 16 horsepower. These pumps are relatively low flow and higher head applications, mostly for residential under 200 gallon a minute applications. They have a cutting mechanism on the inlet side of the impeller that shreds and cuts the raw sewage before it enters into the impeller. And then usually your discharge is between 1.25 inches and 2 inch, which means that you can use small diameter force mains. So instead of passing a 3-inch solid, we're grinding it up, slicing it up, passing it through a small throughlet, and pushing it through a 1.25 to 2 inch pipe in order to keep it moving throughout the system. Dry pit pumps are also a non-clog pump, but they're designed to sit only in a dry pit. They cannot be submerged. You used to see these a lot more in the past, but now most people are using submersible dry pits. As you all know, especially in our geographic area, if you're in a pit and it's supposed to stay dry, eventually it's going to get wet or flood. So we don't use these very often anymore unless they're inside of a plant. Usually you'll see us use the dry pit submersibles. And then you have different styles of pump, like progressive cavity pumps that are made to do sludge. They're going to be a screw type pump that pushes the sludge through, usually very thick viscous material. They're usually just transferring it from one area to another, so it's a low head application. We do not sell these type of pumps, but you do see them in wastewater plants. Positive displacement pumps. These are typically what we see as chemical feed pumps. This particular pump you see is a diaphragm pump. It is going to push fluid from a cavity using a diaphragm. The LMI, the Grundfos dosing pumps are both types of diaphragm pumps. So is a Stenner, a peristaltic pump. It is also a positive displacement because you're squeezing the tubing as you push the chemical out of the tubing. It responds and then allows the flow to come back in. So it is a positive displacement. These are very low flow but high head opportunities with positive displacement pumps and chemical pumps. Another thing that we see but not very often is a self-priming pump. This is a pump that does not have to have what we call flooded suction, meaning that there's pressure or a level of water on the inlet side of the suction pipe. They can prime up to 20 foot. And usually we try to put in a foot valve on the inlet side of the plumbing so that the inlet pipe stays full so it doesn't have to prime all the time. And then also we have sump pumps, effluent pumps, dewatering pumps that you see in our area. So as we talk about pumps, the thing we always do is talk about our hydraulic design point or our duty point. And we're going to talk about how we develop that duty point, what requirements we have to go through to get those duty points, and how we apply them to a pump performance curve. The duty point consists of flow in gallons per minute and head in feet or PSI. So we have to understand as we're designing how we get flow and how we calculate feet. Flow is a condition that we don't have to calculate. It's about the process requirement. Head is something that once we have flow, that we have to figure out by calculations. So we'll talk about that next. So flow, as we said, is something that we don't calculate, but we use as a process. For instance, if I'm designing for a booster station for a small community or a new subdivision that's going in, I consider the number of homes that are being supplied, and we design around the peak design flow for the number of homes required. If you're in a plant, you may be sizing for a filter backwash, and the purpose there would be that the manufacturer will tell you that for proper backwash of your filters, you'll need a certain flow rate and a certain head condition in order to be able to provide that flow rate to your filter properly. Maybe you're in a high service pump and you've decided how much flow you need to pump to the high service tanks to fulfill your requirements to the community, or a chlorinator to pull a vacuum, or fire protection where you need either 500 or 1,000 gallons per minute. But the point is that flow is about the process, not about a calculation. So we usually look that up in tables. We look that up in requirements by equipment manufacturers, but that is an item that we will do by process. The graphic that you see on the screen now is something that I use when I'm designing for water systems in like a booster station. This is what we call the 10-state standards. This is the peak design flow requirements per home if we're designing for flow. If you notice, it's not linear. Obviously, there could be a higher requirement for one home than there would be 50, because not everybody's going to be using peak flow at all times at the same time. So I'll turn to this page, and for instance, if I'm designing for 10 homes, we'll design for a peak flow of 30 gallons a minute. Now that is peak. That doesn't mean that that's what 10 homes are going to use all the time, but I have to design around that. But if I'm up to 100 homes, I only have to do 100 gallons a minute to give an average peak flow for that many homes. Now we'll talk about the second component of the duty point, which is head pressure. Head comes in multiple pieces. The first thing that we consider is our static head, which is our elevation differential. We're always looking to find out what the elevation is at the pump and what the elevation is at the highest home that we're pumping to, or in sewage, maybe pumping into a manhole at a distant site. But that's the first part of head. The second part of head is the dynamic head, which is the friction losses in the pipe due to the movement of flow through the pipe. So when water flows through a pipe or through valves or fittings, there is a head loss that happens as it flows through there. The more flow or the smaller pipe requirements, the more head loss that can happen while the flow is occurring. So once we develop the flow, we use the flow information to calculate the dynamic head as it flows throughout our system. So the total dynamic head is, which we see on pump tags as TDH, is the combination of that static head and that dynamic head, which is when the water flows. So if we talk about static conditions or dynamic conditions, for instance, if you're out at a booster station and I ask you what the static head is, what I'm saying is, without a pump running, without water flowing, what does the pressure gauge show? And then when you talk about dynamic, when the pump turns on, your pressure changes. What is that head condition? That's your dynamic head. So the two of those together make up your total dynamic head. This chart shows a friction loss chart, and I wanted to show this so that you guys can see how important it is to properly size your piping. Many times when somebody is putting piping in to a system, what they think about is the price of the pipe. Yes, you can push flow through a small pipe, but the result is that there's an additional head loss through that pipe, which requires, which shows for a more dynamic head, which means that your head condition is much higher, which requires a bigger pump. So when we look at this, for instance, if you look at the 100 gallon per minute flow in a 2-inch pipe, you look down and you'll see that 100 gallons a minute, it loses 14.53 feet of head through 100 feet of pipe. So trying to push 100 gallons a minute through a 2-inch line is maybe not a great idea. But if you look over at the 4-inch pipe and at the same 100 gallons a minute, you only lose about 0.58 feet of head per 100 feet of pipe. So it may be worth your effort if you have a long pipe run to do 4-inch pipe instead of 2-inch pipe, because you're losing a lot less dynamic head and you can size your pumps much smaller. But that's really important. A lot of times we see problems, especially with chlorinators, because people try to run too small of a line from their chlorinator ejector over to their injection point. And if that line is very long and your pipe size is very small, you can get a lot of back pressure, which means that you're not going to get the right amount of differential pressure to pull a vacuum in your ejector so that you can open up those regulators to get your chlorine flowing. So this is an important information when we're sizing, but I just wanted to give you some understanding of how we look at that. so that you can see what the difference that it makes for choosing the pipe with the amount of flow that you have. I would say this would be a good place to, if there are any questions, Dominica, that have popped in through the chat room, let me know and we can answer some things through now, and then we can move forward.
No questions so far.
Very good.
You want me to do the first poll question or not yet?
We probably haven't got far enough yet, so I'll cue you when it's time.
Okay.
Okay, so the next thing we'll talk about a little bit is head and feet, or PSI. So feet and PSI are both ways to measure head. For whatever reason in our industry, we've always talked about head and feet on a pump curve, but we always put PSI pressure gauges out into the system. So it's real important to be able to go back and forth between PSI and feet. So to remember this by, anytime you have PSI, or you're looking for PSI and you have feet, you take your feet and divide by 2.31. To go the other direction, to get feet, you're going to take PSI and multiply by 2.31. The easy thing to always remember is to remember that 2.31 number, but I always try to remember that feet are bigger than PSI. That's the way I always remember if I'm multiplying or dividing. As many times as I've done this, I still sometimes get a little confused. So I always remember, if I'm trying to get the feet, I got to multiply, and that helps me remember that feet are bigger than PSI. So as we've talked, your duty point equals your flow in gallons per minute at a head in feet, which is your total dynamic head. So you're going gallons per minute and total dynamic head, and that's what you'll see on these applications and on the tags of the pumps. So if we're sizing a booster pump for a booster station, you have to understand your flow requirements, your inlet pressure, because we're just adding the pump pressure to the inlet pressure, your elevation change, which is your static, and your friction losses, which are your dynamic head. So your inlet pressure plus your pump pressure is going to give you your total discharge pressure on the outlet sides of your pump. So what I want to do next is get into the pump performance curve, which some of you guys have seen, but there's all kinds of information that we can understand from these curves. This is a very simple, very normal curve that we see in a book or in a selection process from many of the pump manufacturers. I've actually got this pump out of a Deming pump book that is one of the old books that I still go back to. I want to talk about the different components of this so that we understand how it works. First of all, you'll see, if you can follow my cursor, that this curve that goes along the top is a curve that's called the performance curve. That performance curve is what the pump is the only place that the pump can perform. So when you get a pump, there's no way that it can perform anywhere except for on the curve, depending on some of the information that we see in the system. On the bottom of the curve, you'll see the flow in gallons per minute, 200 gallons a minute, 400 gallons a minute, 1,200 gallons a minute, and then head and feet on the vertical axis. So as we look at this curve, it's going to operate between the red line and where the pump the curve ends, which means that it's going to operate between around 220 gallons a minute and then all the way out to somewhere around 1,800 gallons a minute. So it's only dependent on what the information that it sees with head. As you see here, this specific curve, this impeller has been trimmed from 12 inches to 11.75 inches. So this darker curve here is the actual performance curve for the trimmed impeller. So this pump will only operate somewhere on this curve. So for instance, if we know that we have 60 feet of head in our system, if you travel over and hit this pump curve, at that point, it's going to be able to operate somewhere in the neighborhood of 550 gallons per minute. But if you have only 20 feet of head or 30 feet of head, then you're going to see that this same pump is going to give you close to 1,550 gallons a minute. So the same pump, different head condition, has a completely different performance output on flow, and that's really important to understand. If you notice in this one, in the red triangle here, or red arrow, we have selected a duty point to be 100,000 gallons a minute, 1,000 gallons a minute at 50 feet of head. So this specific point fits very well in the middle of the curve. And the reason we want to do that is because we want to make sure that if we're off in our head calculations, that it still stays somewhere on the curve if it's plus or minus 5 feet of head, but also because we want to fit inside the best efficiency point. So these green curves, as you see them on the performance curve, are your efficiency curves. As in this case, our best efficiency point is 84.1 efficiency, and that's hydraulic efficiency. So we selected a curve, we selected a pump, when trimmed, fits at a very, very good point for our duty point, very efficient and in the middle of the curve. So this will be a very good selection. The next thing I want you to notice is the brown dotted lines as they cross diagonally across this. These are our horsepower curves. And as you notice, that specific point is going to fit below our 15 horsepower dotted line, which means that we'll be able to use a 15 horsepower motor at that duty point. But let's talk about that a minute. You'll also notice that there's 20 horsepower curve and a 10 horsepower curve. As we move back and forth along this curve, and this is where the pump's going to operate, if I move way back to the left on this curve, I can drop down to a 10 horsepower motor, but I'm only going to be able to operate without overloading that motor in this lower end of the curve. Also true, if I have less head and I'm operating somewhere over on this side of the curve, I'm going to overload that 15 horsepower motor. So if I'm going to select a motor that's going to give me an opportunity to be non-overloading throughout the whole curve, I'm going to select that motor to be a 20 horsepower motor so that I'm going to run this performance curve and run that pump with a 20 horsepower motor. So even if I don't have near the head that I think I have, I'm not going to overload that motor at any point. And why might I not have that head? We might have a leak at some point, and the head loss drops. Or if, we might open a hydrant in order to allow a flushing or the fire department to fight a fire. And when we do that and we have less head, we don't want to overload that motor and it get hot and trip out. So we want to choose a motor that's going to be big enough to handle that performance curve. So I'll stop a minute and see if there's any questions about that performance curve. Even though they might look a little complicated, they're not really that tough.
Todd, we had one question from a little bit ago. How is back pressure factored into TBH? Example, connecting to existing FM. It's from Cody.
All right, good question. Good question. So total dynamic head is going to be your static head plus your friction loss. So when we're sizing a water pump, you're pumping usually to a tank or to homes. It's going to be an open end. But if you're sizing a wastewater pump, sometimes you're going to pump into another force main. So or if you're sizing, for instance, a pump for a chlorinator, you're going to maybe pump eventually into a high service pump line or another pressure line. So that total dynamic head is also going to include, at some times, overcoming the pressure that's in the line that you're pumping into. If you're pumping into a sewer force main, or if you're pumping into another line as an injector for chemical, you've got to overcome the static head, the friction loss in the pipe, and then the pressure in the line that you're pumping into. I hope that makes sense. That's a good question.
That's it for the questions for now.
So I want to drop down here to the next curve you'll see, which is another way to indicate your motor horsepower. As you saw up here, one of the ways we see it, and it's easy to display on the curve, is through these dotted lines. But also you'll notice that as flow gets bigger, your horsepower requirement goes up, which is also displayed on this version. But this is a good way to see the horsepower requirements as you go up in flow. This is usually a curve that's at the bottom of your overall curve. As you notice, this curve is going to be at the top of the page with your flow and head. The motor curve is also going to have your flow, and except on the vertical axis is going to have horsepower. So you'll see here, as flow gets bigger, the horsepower requirement goes up, which is why we ended up using a 20 horsepower motor to make sure that when we went into the high flow areas of that curve, that we were still non-overloading. The next curves you'll see are an indication of what happens when you apply a VFD to a pump performance curve. So earlier we talked about the old way. When you trim an impeller, I see that as I trim an impeller, you drop in your performance curve. It drops below the original curve and a little bit to the left. That's the way we used to do a trim, or to personalize a performance curve to a specific condition. Now we do a lot more application with VFDs. So you'll see as you turn down the speed of a VFD at 100%, you're going to get the full capacity of a performance curve, at just like you would at full trim. As you turn down the speed, the flow drops and the head drops a little bit down and to the left. So you're able to be able to pick up different design conditions as you change the speed of your pump. So why would we do that? One of the ways that we hit the demand of a community is by putting in a booster station and try to maintain downstream pressure. So if you have a new community on a hill somewhere, a subdivision, we want to make sure that you always have somewhere around 60 pounds of pressure in your faucets. So what we do is we put in a transducer. The transducer is looking to be able to provide feedback to the control system and change the speed of the pump so that we're maintaining a downstream pressure, which will equate at the end of the line a consistent pressure to the subdivision. So instead of, in the old way we always did it, was having a pump pressure switch differential, which might go up to 60 pounds and then turn off or turn on at 40 pounds and turn off at 60 pounds. So there was a differential. Now we'll try to change the speed of the pump to maintain a downstream pressure in order to have a consistent pressure instead of that differential. It's a much better process. It allows for the pump to run more often, which means that you're not starting and stopping it all the time. And it's able to run at a condition that's a lot less than full speed, which means that in times when there's low demand, you can run way down in here, which is going to require a lot less horsepower and a lot less power requirements to save money on your energy costs. So that's a big deal. The other thing you might do is try to maintain a flow rate. If it's important in a wastewater plant to maintain flow into a plant, you might use a flow meter input back into your control system and try to maintain a flow rate by changing the speeds. As your flow goes high, your pump will slow down a little bit, so it'll come back down, and vice versa. So you'll always work back and forth to try to maintain that downstream flow rate. So that's why we use it in process, and it's also a good energy saver, which is why a lot of people are turning to it. You get the benefit of both. So our system curve is what the next thing we'll talk about. Each individual system is going to have its own curve. And as we talked about, we're going to have the flow rate as we know it, but as flow increases, it's going to get harder and harder to pass through the pipeline. So as we saw on that table, the more flow, the more head loss we get through the pipe. So every system that we look at, as we plot flow versus head, or in this case it says resistance, which is our dynamic head, we're going to get a curve that starts bending upwards, because eventually we're not going to be able to push any more flow through that pipeline. So it's going to get very vertical at some point. But as we are doing design, we start plotting flow through that system. Then we add our static head, and we end up with a pressure curve, a curve that looks as this red line is on our performance curve. This will be our system pressure curve. This is our pump performance curve, and where the two intersect is where your duty point hits. So as we're designing with flow, calculating our head by using our system curve and applying the pump performance curves, we find the place that fits the best in our application to pick a pump from. And this is true in water and sewer. The same ideas are in effect. Now, in this case, if we actually applied our static head before plotting this, let's say we had 50 feet of static head, this curve would start right here and then bend up. So that's the only difference. So let's talk about motors now that we understand the pump. Yes.
We have a question. I don't know if you want to answer it now.
Go ahead.
Water pumps, how many impellers can you add, and where is the cutoff point? And can you add impellers to all water pumps?
So vertical multi-stage and pumps or split case pumps, you can add impellers to. Depending on the pump, it depends on how many you can add. On a vertical multi-stage pump, if you look through a Grundfos book, for instance, you'll see that you have, on some pumps, you can add up to, say, 15 to 20 stages or impellers. On a split case pump, the most that I've ever seen is a 4-stage, and it has 4 impellers added to it. But it's completely dependent on the style of pump, and then you may have to go to a completely different pump application if the number of impellers just doesn't work for you. Hope that answers your question.
One more on sewer pumps. Why do they say they won't clog, and they clog very often?
That's a great question. I wish that that it wasn't so easy to clog a sewer pump. A non-clog pump means that its purpose is to pass solids, but especially in today's atmosphere, with a lot of people struggling to have the right type of toilet paper, many people are flushing things that don't need to be flushed. The sewage is getting much more difficult to pump and keep pumps from clogging. Swiffers, baby wipes, a lot of things that say quote unquote flushable really aren't biodegradable, which means that when they get into the water system or the sewer system, they don't start degrading. So when they get to the inlet of the pump, they're still in their full capacity. And so when all of those get together, along with all the other stuff that's done into a wet well, including grease and all kinds of other things, you start getting what our guys in the field will call a mop head. All those things start going together and creating a solid that gets significantly larger than the 3 inches that we say will pass. Also is true that sometimes you'll get real stringy materials in these tough items like the non-flushables that people flush, that'll get stuck between tolerances between the impeller and the bottom plate. And when that happens, you get one little piece thick and another piece thick, and it starts clogging that up. So yes, you're right. The most inefficient thing about a sewage pump is not just that they have to pass solids. It's that sometimes they get so clogged up that they can't pass any, and that's a problem. And it's the hardest thing for a sewage system to operate in is trying to make sure that those pumps don't clog. Anything else?
Nope, that's it.
Okay, motors. We'll talk about motors a little bit. There's different types of motors: open drip proof, totally enclosed fan cooled, explosion proof, submersible, oil filled, air filled, inverter duty, meaning that it'll work with a VFD, and different types of efficiencies. The speeds are about the magnetic poles. A 2-pole motor is a 3,600 RPM motor. 4-pole is 1,800. 6-pole is 1,200, and so forth. We'll see jobs where we'll do anywhere from 900 RPM up to 3,600 RPM, depending on the application. Voltages, you'll see voltages in 120, 208, 230, and 460, mostly in our world. It does get bigger than that, usually in industrial sites, but generally we see these voltages. Sometimes in a large plant, they'll go up to medium voltage, which you'll see like at 4,000 volts, but usually it's one of these. And then you'll also have single phase and 3-phase, which is very important to making sure we choose the right motor. Single phase can exist in all of these. We normally only see it in 120 and 230, but there is such a thing as 460 volt single phase. We just see it very rarely, but it's very important to know what phase and what voltage we're operating on. When we're ordering pumps or parts and replacing motors, it's important that we get the model number and the serial number off of the motor tag. The frame size, this is something that people sometimes forget. The frame size is an indication of how that motor physically bolts to the pump. So it's really important. You can get different 15 horsepower motors that won't bolt up to your pump because the frame sizes are different. So that's very important to get. Obviously, voltage, horsepower, and phase. The application is going to tell us if it needs to be a submersible motor, if it needs to be an inverter duty motor, if it's TEFC or open drip proof, the RPMs that they're working for. And then it's also important to make sure that we get the shaft diameter of the motor because there's going to be a coupling from the motor shaft down to the pump shaft that we have to tie into. So what does open drip proof mean? It just means that there are cooling vents so that the water dripping does not contact the motor. So these are usually for indoor applications. You might have some dripping inside, but you don't have water spraying or raining on a motor. A totally enclosed fan cooled is going to be a dust type and moderately water type seal. You'll see these used outside or in a situation where you might get a bursted pipe and water spray inside of a booster station, or in a chemical area where you want it to stay the chemical to stay outside of the motors. We typically use mostly TEFC motors, sometimes open drip proof. And then you can also, for wastewater, get explosion proof motors that are defined by UL to prevent ignition if there are explosive gases in the area. There's oil-filled, air-filled motors that we see in submersible pumps. Different manufacturers feel like different types of motors are better for their application. It's really a personal thing. Inverter-ready or inverter-duty motors are made to say that it is able to be run on a VFD. Most new motors are VFD-ready or inverter-ready. Older motors mostly are not. So if you have a customer that's putting a VFD on a old pump, they need to make sure that that motor is sized and inverter ready so that it doesn't overheat the motor. The insulation is different and it will be required to be different for those VFDs. You also have different efficiencies that different motors come in. One thing we didn't talk about, I mentioned to you earlier that in a pump you have a hydraulic efficiency. In order to get your total efficiency, you're multiplying your motor efficiency, which is usually in the 90s, 90% efficiency, times your hydraulic efficiency. So what we call the overall wire to water efficiency is the multiplication of your hydraulic efficiency times your motor efficiency. And that's how you really get the idea of how efficient your system will be and how much it'll cost you to run it. So how do we use the information we've learned? We'll be able to use it through application, troubleshooting, trying to figure out how we're doing replacement parts, upgrades, repairs, and new design when we're working with our consulting engineers. This is a little bit of information that I always like to keep in my pocket when I'm talking to people on the phone. It's a quick horsepower calculation. Horsepower equals flow in gallons per minute times head in feet divided by the constant 3960 times the efficiency, the hydraulic efficiency of your pump. So if you're looking at a system, you can, if you have any of these and are missing one, you can use this equation to solve for the other. It's very nice for me to quickly be able to do that if I have a little bit of information. So Dominica, I did forget to tell you to send out those questions. I apologize. That's why we're having this run through. If you would send those questions out. We've run about an hour in our presentation. As I said earlier, the requirement for the CEH credits is to be able to show participation from our operators. So I put together a few questions for you guys to answer. They're relatively quick to go through. If you would go through, submit them back to Dominica. We're going to learn from your submission how it looks on our end and what we do with that information.
I just launched the first question, so you guys go ahead and select one of the answers if you could. Todd, this is the first question. To go from PSI to FT, do you multiply or divide by 2.31?
Right. Okay, I'm going to go through each one of these as she sends them out.
There's 75%. Somebody still hasn't voted yet.
I might give an answer to somebody then. So to go from PSI to head, you multiply. If you get a pressure reading from a pressure gauge, and we need to figure out how much head we have on a pump curve, which is in feet, multiply that pressure by 2.31, and that'll give you your total head in feet. Question two.
Question two, I haven't done that one yet, so let's do that one. You guys go ahead and do the voting really quickly, please. All right, couple more seconds, then I'll close it.
Okay, the question is, does the amp draw for a pump motor go up or down when head increases? So if we look back, if we think back on our pump performance curve, as head was higher, flow was lower. And as head goes down, our flow goes up. So the more flow we have, the more opportunity, the more horsepower requirement we have based on our motor information. So that means if we have high flows, we will have high horsepower requirements, which means we'll have high amps. But when our head increases, the flow goes down and we'll have lower amps. So let's think about that for a minute. Let's say that we are in a booster station and somebody has partially closed a valve out in the field. One of the things that we'll notice, obviously flow will go down. If there is a flow meter, you'll see that. But the other thing you'll indicate is if you have SCADA that is monitoring your amps will go down because you've got more head on your system. Your flow rate goes down, therefore your amps go down. So it's a good way to start seeing things happen in your system. If you have a wastewater system and your check valve gets clogged up by sewage, your amps are going to go down. If you have a clog in your pump, that's different. You're restricting the turning of your impeller. Then your amps go up. But if your head pressure goes up on your discharge side by a clog or a valve being shut, then your amps are going to go down. The opposite is also true. If you have a leak or a hydrant that's opened and your head goes down, your amps are going to go way up because your flow increases. So that's going to be an indication of a leak. So that's a good way to see that. Question 3.
Okay, just launched. You guys go ahead and select if you could.
Okay, the question for number 3 is, what are all the different components of a duty point? Our options are flow, static head, dynamic head, horsepower, and amps. So we talked about flow being the first part of a duty point, which we figure out by the process. Static head is going to be your elevation change, and dynamic head is going to be your friction losses. Those are the 3 that are part of the duty point. Horsepower and amps are going to be things that you apply a motor to and that you measure based on the application. But the parts of a duty point are your flow, the static head, and your dynamic head. And then, yes, per Cody's question earlier, back pressure in the line you're pumping into will be part of that head requirement that'll have to be also considered. So question 4.
Okay, let me share it. You guys go ahead and select if you can.
So question 4 says, on a pump performance curve, what changes the flow output for the pump? Discharge head, horsepower, voltage, or suction pressure? So the answers we're looking for on this one is discharge head and suction pressure. So first of all, we know that discharge head, as it changes on the pump curve, it changes the flow rate depending on where it operates on the curve. But also suction pressure makes a difference. Let's think about pumping out of a sewage wet well. When the wet well is completely full, you have more suction pressure, meaning that you don't have to create as much differential pressure with your pump. When that wet well is pumped down and you have less suction pressure, you have less pressure on the inlet side, which means that you have to pump more discharge pressure with your pump, excuse me. So both your discharge head and your suction head or suction pressure make a difference on your flow output. Horsepower and voltage are things that are going to be part of the equation of selection, but it's not going to change your flow output. Okay, question number 5. List the items that are needed to assist in pump selection. Dom?
Yes, I just ran the poll, so you guys go ahead and select the answers, please.
So the question is, list the items that are needed to assist in pump selection. Application, power, context, pump and motor tags, flow, head, pictures, dimensions. The answer is yes. All of these things are important. if you're in the field and you can get as much of these answers as you can, it is very helpful to us when we're doing application. And context is very important. A lot of times I'll get pictures of tags and can we do this, or do we have something that'll replace this? The tag gives you the flow and the head and sometimes motor information, sometimes full load amps, but it doesn't tell you what the application is, and it doesn't tell you the context surrounding the requirements. So as you look through these, and I'll go back up to them, when you're out there looking at these applications, try to go through this list of information, and that is golden. Pictures and dimensions. When we're trying to fit something back in to an existing application, seeing how we have to make modifications to the plumbing, checking about how the lay links are going to fit, very important. So the answer to this one is yes, please get all of this information to help us in selecting a pump to replace something that's out in the field that's existing. Question number 6.
Okay. You guys go ahead.
Okay, question number 6 says, if there is not a pump tag, how can you get information in the field? So an easy way is to check flow meters and gauges. So your flow meter is going to give us our flow rate that we're looking for. Your pressure gauges are going to give you discharge pressure and suction pressure. And I would like to see the gauges know when the pump is running, what does the suction pressure say and what does the discharge pressure say. That'll give us static readings and dynamic readings with the pump running and not running. The other things are there's stickers in the panels, and most of the time these stickers are going to tell you the horsepower. They're going to tell you the voltage and phase, and a lot of times they're going to tell you the full load amps. So that's information. If you open the inside and look at the inside of the door, you're going to be able to see the sticker that gives that information. And then if very few, but some of our customers do a good job of keeping their manuals. If they do have manuals or an old submittal or something that gives the information, it would be great to go back and look in their drawers and the manuals from when they had the system built and see what they have to offer. But those are tools that we can use to get the information if they're not on a tag, or if your customer doesn't know that information, we can get this stuff to start doing application. So in review, we learned about many different types of pumps and motors. We learned about pump performance curves, which I think is something that's not as complicated, but it's been a little bit scary for people to look at. We learned how VFD affects performance, and we learned how understanding simple hydraulics can help in troubleshooting and in pump selection when we're trying to figure out an application that we need to do. I hope that this information will arm you with better decisions, troubleshooting in the field, communicating with your team, your consulting engineers, your boards, your engineering department, and make you a better, more valuable water system employee. I just looked down at my clock and we are at 11 o'clock on the number. I hope if there are any questions, we can answer those.
If you guys have any questions later you can think of later, or if you have any suggestions for us on how to do this better, please shoot Todd or I an email. Thank you all, everyone. Have a great weekend. Thank you, Todd.
Guys, bye-bye.
Bye.